Okay, so question number 4. We have this logarithm, got a restricted domain from -1/2 to 1/2, so therefore they're asymptotes. It's the logarithm. I could combine those two logs together if I wanted to by going log base e of x plus 1/2 over 1/2 minus x. What is the range? It's asymptotic. All real numbers will be the range. Find the derivative. So I want the gradient at that point there. It looks like about 1, but let's just check it. So let's enter this in the calculator. So bring up my keyboard, get my face out of the way. Log base e of x plus 1/2. Not typing very well now. X plus 1/2 minus log base e of 1/2 minus x. Beautiful. And if I take the derivative, and take that answer and make x equal 0, I get 4. So it's equal to 4. There's two answers there. So d dx of f of x equals -4 on 2x plus 1, 2x minus 1 when x equals 0. So that will give me my method mark. Find the maximal domain over which f is strictly increasing. The maximal domain where it is strictly increasing. Strictly increasing. It's going to be strictly increasing for all of the domain. So it's going to be -1/2 through to 1/2, non-inclusive, because it's asymptotic. So the next part of the question asks me a question about this. Now this is the same as f of -x equals -f of x, therefore it is an odd function. We're going to show this an odd function. And the way they're asking it is to turn it into an equation. That's okay. So I know that f of x is, if I take my inside here, and I'll simplify that answer. No, it's okay, don't. So f of -x will equal, if I put a negative there and I put a negative there, it's going to equal log base e of 1/2 minus x minus log base e of x plus 1/2, and negative f of x equals log base e of 1/2 minus x, and then minus this one, minus log base e of x plus 1/2, therefore equal. Therefore f of x minus plus f of minus x equals 0. So it's a straightforward show that. However, what they wanted you to know was that this is an odd function. And I think the reason they wanted you to know that was that what we have here, if you reflect over there and reflect over there, you get the same shape. So it's a symmetrical function that if you put it down here, but you also put it across there, you'll get the same result. So find the domain of the rule of the inverse of the function. Okay, so if I grab my original, so that was without the negative there and without the negative there, and I try and put a y there, and I try and put a y there, and I make it equal to x, can I go solve for y? I can. So the inverse is e to the x minus 1 over 2 e to the x plus 1, and the domain will be the range, therefore the domain is all real numbers, which, by the way, is why they asked you way back in part A, what was the range of this function, to help you answer this particular question. It's worth 3 marks. I've just got the 2 answers. What I might do is I might say domain of the inverse equals the range of f, therefore R, there's my method, and also f of x, y equals f of x, swap x equals f of y, and gives me that. So I've got enough to show them what I did to come up with that answer. And lucky last, let me have this function here where I have the same domain, but I've got 1 on k log base e of the same function, and the inverse is e to the kx. The areas of the region bound by the functions h and h negative 1 can be expressed as a of k. A of k is the area of the trapped function, and k is an element of all real numbers, but k is positive. Okay? You are not required to find or define a of k. Determine the range of the values of k such that the area is bigger than 0. So there must be some point where the areas don't overlap. So I need to find the value of k where the areas don't overlap. So we have our original, which is a logarithm, and we have our inverse, which is an exponential. So this is a kissing. This is a kissing function. So it's going to be a kissing function. So I'd like to grab this function, which is my exponential, and I've got k there, and I've got k there. Is that correct? K there and k there were the 2 at the front. So if I was to go calculate the derivative, and I'm going to make x equal 0, sorry, because that's where the intersection point here is, given x equals 0, and k on 4 will be the gradient at x equals 0. For it to be kissing, I want that gradient to be 1, so that my logarithm and my exponential both have the same gradient of 1. Therefore, k equals 4 is where they're kissing. So if I was to do, so I make that worth 4, and make that worth 4, and I take this and drag and drop it. That's my exponential, and my analysis is sketch the inverse, which will give my logarithm, and there's no trapped region. There is no overlap, because at the point of intersection, they're both the same. If I was to make that equal to 6, and make that equal to 6, I pressed X so that when I drag and drop, I lose the graphs that were there before. Analysis, sketch, inverse. Zoom out. I now have trapped regions. So determine the range of values of k. So k being bigger than 4 will be the values of k. Explain why the domain of a of k does not include all values of k. All values of k is everything bigger than 0. For k going from 0 to 4, there is no trapped region. Therefore, a of k equals 0. Just to confirm that, if k equaled 2, and that was equal to 2, I'll press XE, then I'll go and pick this up, 2 and 2, and I then analysis sketch the inverse. There is no trapped area. Zoom out. Now I know that because this kissing function idea, that where they just touch, both of them have a gradient of 1. So that's where I got this setting equal to 1, and that's how I was able to find the value of k. And that's all for question number 4.